Well, we're studying stars, so we might as well look at the one that is so important to us that our ancestors thought it was a god. Maybe the primary god, maybe not the primary god. Depends on your stories, right? People thought of it as a god. The Egyptians called it Ra. The Incans called it Inti. Helios was the Greek name. Sol was the Roman name, Latin-based languages, Sol. See if I got this right. I think the German was Suna, and then Sona, I think, was the Anglo-Saxon, or maybe that's flipped. And then you get sun out of that. So it's about halfway out in our Milky Way galaxy that doesn't look like this model, the Milky Way galaxy, because they didn't know. They thought it was a spiral. You heard the story. And we're about halfway out, so here we are. And we think of ourselves going around the sun. Now, that's good. But then people realized that it was heliocentric. They didn't realize we were in galaxies until about 100 years ago, and then to realize that the galaxy is spinning. So the sun and the solar system is moving around the center of our galaxy at about, traveling about, 450,000 miles an hour. That's, 500,000 miles an hour would be 500,000 miles an hour. So you can think that, 500,000 miles an hour around the center of our Milky Way galaxy. Our Milky Way galaxy moving at about 1,000,000 miles an hour. 500,000 miles an hour, and then 1,000,000 miles an hour. Anyway, you can look that up and see where that comes from, and something, all crazy stuff. But for us, we watch it and it seems to rise and set. The God's sun, giving us light, giving us seasons, giving us tomato plants. It's the only star we can get a spacecraft to in a human lifetime. It's the only one. And there are lots of space. So there are missions, key missions to search. SOHO, 1995, to give you a little sense. You don't have to memorize that, of course, but SDO, check that out. 2011, Parker, 2018. Man, good stuff. Just do a little search, have a little fun, look and see what they see. I'll show you some pictures of that. So I'm going to come back to that, but wanted to show you this here too. If you look, if you just say missions to study sun, you could just look this stuff up and have a little fun, right? Sorry. Just search that and you'll see it. And then there's all these missions, right? You could just go through and study all these SDO, right? And then it gets older and older missions, and then it goes down to current missions, and you could do the Parker Solar from NASA. Parker Solar Probe, man, crazy. All the details that we're learning more and more about sun, because we can get to that star. We can get to that star, and I'd like to bring you over here. I'd like you to take a look at our sun. Not outside, not good for your eyes, right? But let's look at our star. And I want you to think of it like we did Jupiter. Remember, Jupiter looks like maybe it's a solid marble, polished marble, or wood or something, but in fact it's a big gas ball. Not big enough to be a star. We need about 75 of those. But it's spinning. Remember that differential rotation? We'll come back to that. It's a big gas ball. The thing different about Jupiter and Sun is that Jupiter has a solid core inside. Sun doesn't have any solid. It's a star. It's a star. But that gas is moving. Okay, this is time lapse, and you can check that out if you want. But that's the time lapse. It's pretty darn cool, right? Now it's going backwards in time. Let's go forwards in time. Crazy. And you put filters on so you can see different features. There's lots of features in here. We're just going to focus on a couple. And then I'm going to leave the rest to you. So what can we say about our star, the life-giving sun? Well, it's a big star on the low mass. It's a big low mass star, so it's in that group, the 6 foot to 5 foot, as I like to analogize. But it's a big low mass star. It's a low mass star. Its total lifespan is about 10 billion years. Most of that life will be on the main sequence, as we described. We'll talk about that in a second. And the current age is 4.6 billion, about 5, so we're about halfway through to life, right? Midlife crisis. It will die in another about 5 billion years. Again, it's still in the main sequence, and it will be till near the end of its life. It's got 6 layers, and we want to say you should be able to name the layers, just a quick sketch, and what's going on in each. Let's do that a little bit. And a couple of key features. And that'll be good for our sun, and I'll leave the rest for you. Let's take a look at those features. Let's take a look at the layers first. All right, yeah, Earth had 6 layers too, but very different. Very different, right? Very, very different. So it's got 3 layers we call the interior layers and 3 sort of atmosphere layers. The whole thing is gas, anyway, all the way. This is not solid, right? Make a note, not solid. Not solid. No solid. No liquid. It's all gas. It's gas. Okay, remember that. So I sometimes have people draw that on an exam, and then I see a solid core, and I'm thinking, this isn't Earth. Remember, we can get 100 Earths across this thing. This thing's huge. Huge. Where is it? If that was sun, then Earth would be a grain of sand. 100 Earths across. Right? Okay, what would Jupiter be? Jupiter would be smaller than this. Smaller than this. Okay, so these are the layers. Now, how are you going to remember these layers? Oh my goodness. Well, memory aid. You could use it if you want. You can make your own up. Here's my memory aid. This is the core, the radiative zone, the convective zone. You could say radiation zone if you want, radiative zone, convection or convective zone. Photosphere, chromosphere, I left that off so that you fill it in with your head, and corona, which I've got to add something to, so we'll see. The core, so here's my memory aid. Can really cook, because it's hot, so it can really cook. What would you like to cook? Well, it can really cook pretty crispy chicken. I mean, you know, you put some chicken on that star, it's going to be pretty crispy. I don't know. Can really cook, but now you got to know what it means. Can really cook pretty crispy chicken. Nice kind of three phrase. All right, so what's going on here? What is going on, Marvin Gaye? Well, in the core, you know, it's a main sequence star. It's in the main sequence first stage. Remember the bag of glass. And so what we have here is we've got a big balloon factory. 4 hydrogens, or protons really, are squeezed into, in a sequence, but I won't get into that, 1 helium. It's a balloon factory, and when that's done, when we're done making helium, we'll go into another phase. Most of its life will be doing that. And as it does that, where's my purple pen? I seem to have left the house. Oh, I want purple. I think this purple's dead. All right, not very good. Yeah, I think I left my purple pen. Okay, imagine purple. I'm going to use blue. Sorry. that fuses, right? So that's fusion. And it snaps together. And you know what happens when that snaps together? That creates light. This is the equivalent of about, in some ways it's kind of slower than you might think, but it's still the equivalent of about 1 million hydrogen bombs each second. And each of those snaps, although it's a sequence, but it's going to create light. So that's what's going on in the core. Its main sequence, every star starts its life that way, and every star lives most of its life doing this. Next phases go faster. Okay, and so that creates light. That leads into here. So the radiation zone is where that light, or radiative zone, the light pushes out, in a sense, right? So the light pushes the gas out. Now the light gets tired. So even though it starts out as gamma, high energy, it starts losing the energy. Might get down to X-ray, and then maybe some of it get down to UV, and maybe some of it will get down to visible. Interesting. It could take, I think it's like 150 years for the light to get out. It's got to go through the gas and hit the gas and all this, about 150,000 years to get out to here. And then what happens here? So that light radiator zone, light pushes out. We got that. Well, you got this gas, it's hot, it's kind of, so this is kind of like Earth, right? But it's not, because Earth has that metal and rock, solid stuff. But nonetheless, convection means the hot stuff rises up, cools, and sinks. And that pushes the gas out, right? It sinks. That's what's happening, convection. We've talked about. A lot of things come around, don't they? The tidal effect, all those sorts of things. There are a lot of basic factors of physics that relate to astronomy. All right, so that's the convection zone, that pushing the gas out through convection. And then what's going on over here in the atmosphere? The photosphere, the chromosphere, and the corona. I won't say too much. There's a lot of interesting things, a lot of research done out here. So let me work backwards and then finish it over here. And this is what we're going to do. So the corona is like a crown. Now we know about the coronavirus. And if you look close at the virus, it's got these little things all around it that look like crowns. That's why it's called corona. This is the crown. And in fact, it goes way, way out. I'll show you some pictures here. We'll do a little slideshow after we cover this, okay? All right, so we'll do the slideshow in review. So what you find, and you saw this spinning ball of gas, right? This is the source of what's going on. We'll talk about that. Remember, it's in hydrostatic equilibrium, right? It's in the main sequence. It's in one fusion cycle. Gravity's pulling it in, but this is pushing it out. That's what we meant by hydrostatic equilibrium. Gravity's pulling it in, and it would collapse, but this is pushing it out to keep it from collapsing. And so it's in balance for a long time. Whew, good thing, right? We should step outside and show you a blue sky and that blue sunlight scattering around outside, bouncing off. I can see it outside, right? From that star there, 1 AU away. 93 million miles. Okay, so we got the crown here, and that's this gas out here, and people study the temperature and all kinds of things. It goes way, way out. You really can't see it. You'd have to cover up sun in your telescope or somehow block sun, solar eclipse works, and then you can see that corona. We'll talk about that. This is the chromosphere, sort of called the sphere of light. No, sorry, my head was going over there. The sphere of color, you can see I did that. The sphere of color, chromatic, anyway. And here the photosphere or sphere of light, pretty much what you see, not this, but here and here. So that, not too much detail here, and again, I'll let you go, but let's let you go into it if you like. Let's get down to it. All right, I'm going to show you some pictures, okay? I'll let you rewind. Nah, fine. Fine, all right. I'll show you the pictures now. And then we'll come back. Zoom in. I think I can make this better than I did before. Okay. This is a cloud of gas, colorized. Hubble Space Telescope, wonderful. A cloud of gas in our galaxy. And within this cloud, how big is this cloud? See, you can't tell. How big is this cloud? I don't know. Is this in your sky? Or what? No. Out of this regions, you'd form multiple stars, solar systems, right? And they pull on each other and they kick each other out, whatever. So these, remember we talked about in the galaxy, these giant gas clouds form many stars. So that's the beginning of our life there, right? And then, we've got a range of stars. Some big, some small, some hotter, some cooler, some older, some younger. We know how stars form, the basics of that. Nice little review there. Telescopes. We can go to only one star, and you know which one it is? Our star. And remember, about 10 Jupiters across. You need about 75 to make the smallest star, about 1,000 to make this star, Ra, Inti, Helios, Sol. 10 across this way, times 10 this way, 100, times 10 this way, 1,000 Jupiters. Each Jupiter, you get 10 Earths across, about 10, 11. So you can get about 100. So Earth would be a little thing, a little round circle there. How's that for a storm? Crazy, right? So visualizing that, you get a sense of the scale or size. These things are quite enormous, right? And it's moving, it's active. So occasionally it'll spout off, flare up, and send that stuff our way. Thank you, magnetic field, right? From the what? From the liquid iron core, right? You see that? The liquid iron core. So all those connections. Where are we? Now you can look at it in different light. So sun is giving off a lot of frequencies of light, and so you can use different instruments, ultraviolet or whatnot, and to bring that light into an image, although I am having a little trouble there, we colorize it. If it's ultraviolet, we can't see it, so you have to turn it into a color image with visible light. So we just translate that with a computer program. Some periods are more active than others. The last one not so active. Now we get lots of activity. So it goes through cycles of activity. And you can see these. That's an X-ray right there. Right? That's X-ray light turned into visible light. And there we have, can really cook. Core, where the fusion takes place in the main sequence, A for a main sequence star, no matter how big. Radiative zone, where the light pushes out. Convection zone, where the gas then rises and sinks and pushes out. I'm not going to go into that. It's got layers, and we study them, and people try to figure that out. Astrophysicists. If you cover it up with a mask, you see the corona going way, way out, but it's not super bright comparatively. If you were to put sun, this is cover up in your telescope, sun would be that big, and if you want, you can put a picture of sun in there to kind of imagine that. So flare-ups, pretty crazy, and they send our way. Now we look here and we see sun. Now you start to see that it's kind of got light and darkness to it. Light and over there on the right, you get a little dark spot there. What's up with that? Light and darkness? Let's get up close to that. You gotta use filters. Oh, look at that. It's kind of granular, isn't it? Any solid? Any leaks? No, not at all. Not at all. All right? Can really cook pretty